This opening slide introduces rare earths as strategically vital materials for the modern economy. The key point is that rare earths are not important because they are geologically unique, but because they are essential to advanced industrial systems and difficult to mine and process economically. They sit at the intersection of clean energy, advanced electronics, defense, and geopolitics. This slide also frames the broader session purpose, understanding not just what rare earths are, but why they matter so much in global industrial competition. That strategic framing is important because rare earths are now discussed as both an economic and national security issue. This slide clarifies the common misconception around the word rare. Rare earths are generally not scarce in the Earth's crust. The real issue is that economically concentrated deposits are uncommon, and turning ore into commercial products is technically difficult. The slide also emphasizes the three major production challenges. Separation is chemically complex, processing is capital-intensive, and environmental management is sensitive because refining can produce difficult byproducts. That is why rare earths are strategically important, even though they are not geologically rare in the simple sense. The bottleneck is economic and industrial, not just geological. This slide defines rare earth elements more precisely. There are 17 total elements in the rare earth family, the 15 lanthanides plus yttrium and scandium. The slide also introduces the two main categories: light rare earth elements and heavy rare earth elements. That distinction matters because heavy rare earths are generally scarcer and often more strategically sensitive, especially in advanced magnet applications. The slide's purpose is to give the audience a clean scientific framework before moving into strategic and industrial uses. It is the foundation for understanding why not all rare earths have the same economic value or strategic importance. This slide focuses on the rare earths with the most strategic commercial use cases. End and PR are central to high-strength permanent magnets used in EVs, wind turbines, and robotics. Di and Tb are critical for heat-resistant magnets that can maintain performance under high temperatures. Sm is important in aerospace and defense through samarium cobalt magnets. La and Ce serve catalysts, battery-related functions, and industrial uses. Y and Eu are used in phosphors, lasers, and advanced displays. The key point is that rare earths are not one single market. They are a family of materials with very different strategic roles. This slide broadens the application picture. Rare earths are critical in permanent magnets, high-end electronics, precision industry, and military systems. Permanent magnets are especially important because they drive EV motors, wind turbines, and robotics. Rare earths also support semiconductors, catalysts, specialty glass, polishing, displays, missiles, drones, and defense systems. The final panel is the most strategic. Rare earths are now a focal point in global industrial supply chain competition. This means the discussion is no longer only about materials science. It is also about who controls the technologies and value chains of the future. This slide takes a closer look at 4 critical magnet rare earths. Neodymium is the core material for EV motors, wind turbines, and robotics. Praseodymium is commonly used with neodymium in high-performance permanent magnets. Dysprosium is important because it allows magnets to retain performance at high temperatures. Terbium supports stability in those same high-temperature magnet systems, although it is rarer and more constrained. The key message is that the magnet rare earths are the strategic center of the whole rare earth discussion. They are what link the sector directly to electrification, automation, and military applications. This slide covers the next group of important rare earths. Samarium is crucial for samarium cobalt magnets used in aerospace, defense, and high-temperature environments. Cerium and lanthanum are widely used in catalysts, battery-related materials, polishing compounds, and optics. Yttrium and europium matter for phosphors, lasers, displays, and specialty materials. Scandium is more niche, but strategically important in aerospace and advanced materials. The key takeaway is that rare earth importance is not limited to magnets. Some are essential in broader industrial, electronic, and specialty applications that are still strategically sensitive. This slide explains why rare earths are critical. First, they are difficult to substitute in high-tech applications without sacrificing efficiency, performance, or product design. Second, supply chains are highly concentrated. The slide shows indicative IEA-style concentration levels of about 86% in mining, 97% in refining, and around 92% in magnet materials among the top producers. Third, their strategic value extends to EVs, wind power, national defense, and future industrial systems. This makes rare earths a classic critical material story. Hard to replace, hard to diversify, and essential to industries that governments increasingly treat as strategic. This slide expands on substitutability risk. Rare earths are hard to replace because there are limited alternatives in the highest value applications, especially permanent magnets. When substitutes are used, the result is often lower efficiency, larger and heavier components, higher energy loss, higher cost, and weaker long-term reliability. That is why these materials are not easily interchangeable. The key point is that the strategic value of rare earths comes partly from their performance advantage. If a substitute reduces the quality of an EV motor, wind turbine, or defense system, then the original rare earth input becomes much more strategically valuable. This slide highlights where the real bottlenecks sit in the rare earth industry. The value chain includes mining, separation and refining, metal and alloy production, and finally, magnet manufacturing. The key message is that the bottleneck goes far beyond mining. Even if more countries develop rare earth mines, strategic dependency remains if separation, refining, alloying, and magnet production stay concentrated. The chart also emphasizes the extreme concentration shown in IEA data, with roughly 86% mining concentration and about 97% refining concentration among the top suppliers. For investors and policymakers, this is crucial. Mining alone does not solve the strategic vulnerability. This slide focuses on China's dominance in magnet production. Based on the presentation's IEA figures, China accounts for around 92% of global magnet material production and about 94% of sintered magnet manufacturing. That is a striking level of concentration. The strategic implications are clear: high supply chain dependence, vulnerability to disruption, and a problem that extends far beyond raw mining into processing, manufacturing, and technology. This is why rare earths are widely seen as a critical industrial policy challenge. The market does not just need more mines, it needs alternative downstream industrial capacity. This slide shows why rare earths are essential to strategic industries. They sit inside EV traction motors, offshore wind turbines, defense electronics, aerospace systems, industrial automation, and high-end robotics. In other words, rare earths support both the energy transition and the future of advanced manufacturing, while also remaining indispensable to defense systems. This combination is rare. Few material groups are simultaneously this important to civilian technology, green energy, automation, and military capability. That is why rare earths have become a strategic material class rather than just another mining subsector. This slide brings the geopolitical dimension into focus. Control over rare earth supply chains is increasingly seen as control over the industrial systems of the future. The discussion now centers on who dominates the value chain, who achieves national security independence, and how rare earth concentration shapes global tensions. The slide highlights the broader policy debate. Countries want mine-to-magnet independence because rare earths are now considered central to both industrial competitiveness and defense resilience. This is why rare earths have moved from a niche commodity topic into mainstream geopolitical strategy. This slide explains the current geopolitical landscape more directly. China's dominance covers upstream processing, separation and refining, and downstream metal, alloy, and magnet production. The slide indicates China leads heavily in upstream processing and holds a dominant downstream position as well. In response, countries such as the US, EU, Japan, and Australia are treating rare earths as a national security concern and are pushing for supply chain diversification. The key takeaway is that the world is not only trying to secure access to rare earth ore, it is trying to build alternative end-to-end industrial ecosystems. The final slide summarizes the whole argument. Rare earths are critical and hard to replace. Supply chains are concentrated and vulnerable, and countries are now trying to build more independent mine-to-magnet networks. That means the future policy focus will likely be on diversification, resilient supply chains, domestic investment, and international partnerships. The strategic importance of rare earths is not fading. It is increasing as electrification, defense technology, robotics, and advanced manufacturing expand. The big message is that rare earths are no longer just a mining issue. They are a strategic industrial and geopolitical issue.